We've thus far talked about forces and conservation of energy as if energy is always conserved, and we know in some cases that energy actually does get dissipated. That's not to say that goes away altogether, but we have to differentiate amongst different types of energy along the way we have between potential and kinetic. There are also the designation for mechanical energy, that kind of energy which has the potential to make kinetic energy, or it actually already is kinetic energy. There are other kinds of energy, however, like thermal energy, the energy of heat. And we know that there are some forces like friction that actually dissipate mechanical energy. All we have to do is think about rubbing our hands together, and we're taking mechanical energy, the motion of our hands, and we're transforming it into heat. And anyone who's ever had to rub their hands together in the winter knows that you make heat when you have friction. And by the same token, someone who's running along and sliding into home base knows that you generate heat when you slide, or when you get carpet burn. That's the production of heat due to friction. So friction is somewhat different from some of the other forces that we've talked about in that it dissipates mechanical energy and turns it into thermal energy. So we need to do then a somewhat more elaborate procedure when there are non-conservative forces like friction, forces that result in the non-conservation of mechanical energy. In these cases, we will have to effectively think of mechanical energy as a bank account, and whereas up until now we've had a constant amount of energy in that bank account, when there is friction or a non-conservative force like it, we must think of debiting the bank account by that amount in order to make the books balance. Again, it's not the case that friction really makes the energy disappear altogether. It's just that it's no longer a mechanical energy, it goes into the form of heat. In an example like this roller coaster problem that's shown, it would have been typical to apply the conservation of energy and say that if a cart was released at the very top of the roller coaster and initially had lots of gravitational potential energy, that would be converted into kinetic energy at the bottom of the roller coaster. We're going to consider now a slight variation on that problem where the cart is rolling along on frictionless surfaces for most of its travel, but then it's right in the middle of the path of the track. There is a flat horizontal section which has friction, and we'll suppose that in that 3-meter long section there is a coefficient of kinetic friction which is equal to 0.5. And we must then develop a somewhat modified solution or strategy for the solution where we use the non-conservation of energy to balance the books and calculate how much kinetic energy is at the bottom. But to see how we do this slightly modified procedure, let's go through the old solution as if there was no friction whatsoever. So we imagine a cart starting from 10 meters off the ground and falling or rolling down to the bottom and converting potential energy into kinetic. Our old solution would have used the conservation of energy, kinetic plus potential at the top of the track equals kinetic plus potential at the bottom. At the top of the track, if we let the cart go from rest, then there's no kinetic energy. It is 0. And at the bottom of the track, if we have fallen all the way through that 10-meter height, we would say that the potential energy at the bottom is 0. Then we would have the conservation of energy is mgh at the top for the potential energy equals 1/2 mv squared at the bottom for the kinetic energy. If we were told the height, then we could solve for the velocity at the bottom. We would notice that the mass cancels out altogether in this equation because we can divide by m on both sides of the equation. And we would derive that the velocity at the bottom is equal to square root of 2 times g times the height. It doesn't really matter the shape of the track. Any old shape of the track that has a height of 10 meters will result in a velocity at the bottom of square root of 2gh. For a height of 10 meters, we find that the velocity at the bottom is approximately 14.1 meters per second. Now that's the old solution, and that's the case where there's no friction whatsoever. If we then need to employ the fact that there is some friction, we need a slightly modified solution. So what do? In the new solution, we would say that we have energy at the top, kinetic plus potential. Then we're adding some work to this problem, where who is doing the work? It's friction that's doing the work. And that equals the energy at the bottom. At the top of the track, as we said before, there's no kinetic energy, there's just potential. And so now we say U at the top plus this work done by friction is equal to kinetic energy at the bottom, because the energy at the bottom includes no potential energy. Well, what is this work done by friction? Friction always points against the direction of the motion. So if work is force, the vector of force dotted into the vector of displacement, then the angle between those two is always 180 degrees. D points in the forward direction to the right in this picture. The friction force is always pointing to the left because it's opposing the motion. And so when we compute the work done by friction, it's going to equal minus mu times the normal force times d. And the potential energy at the top is still mgh, and the kinetic energy at the bottom is still 1/2 mv squared. Now we can solve. If we're given the kinetic coefficient of friction, and we're given this distance d along which there is friction, we can solve for the velocity at the bottom. Once again, the mass of the cart will cancel out altogether. And if we solve, we find that the velocity at the bottom is equal to the square root of 2 times g times the quantity h minus mu times d. This is an interesting solution because if it has some good similarities to our previous solution. In other words, if we set mu equal to 0, there is no friction along that horizontal section, we get back our old result of square root of 2gh. So that's somewhat intuitive. Likewise, if d was 0, that distance along which there is friction is vanishingly small, we get back our old result of square root of 2gh. Now, if we plug in some numbers, the height of 10 meters, the distance of 3 meters along which there's friction, and the coefficient of 0.5, we find that the velocity at the bottom is 13 meters per second. That is somewhat less than the old form of 14.1 meters per second, and that's because the kinetic energy at the bottom of the track is less in this case than it was when there's no friction. Why is there less kinetic energy at the bottom? Because some of the total mechanical energy of the system was debited away. It was reduced by the work done by friction. And notice that in our equation, we added the work done because the work actually is negative. The work done by friction has the effect of trying to slow the object down because the force of friction points against the direction of motion. So whenever we're confused about signs and positive and negative signs, always think that friction is trying to reduce kinetic energy. And if you're ever in doubt and you come up with a result that's a velocity that would be bigger than if there was no friction, then you've made a minus sign mistake. In this case, I literally had to think through which sign was it that would reduce the kinetic energy at the bottom of the track. We will have a number of problems in our future where we are doing conservation of energy problems, but we must factor in the work done by non-conservative forces like friction.